Okay, hi. This is just a little follow-up to show that the test statistic used in the small sample test for difference between population means is t-distributed, and to show it has the correct degree of freedom. So suppose I have two populations, population 1, population 2. They're both normal. Two samples from them, they're both normal. One with mean mu1, one with mean mu2, and they both have the same variance. That's important. Okay, the first sample has N1 items in it, N1 outcomes. The second has N2 outcomes. And we set T equal to this. It's the difference in the sample means minus the difference in the population means. And then I divide by the pooled standard deviation, and then also by this 1 over n1 plus 1 over n2 to the 1/2 power. This is then t-distributed with n1 plus n2 minus 2 degrees of freedom, where SP is the pooled standard deviation. As I said, it's defined that way as a weighted first, you get the pooled variance, S squared P, which would be the weighted average of the two sample variances, and then you take the square root of that. Okay, so it's not too bad. We do this the way we would do just the one from example 1 as well. Once you have it, though, then you can show that under H0, if H0 is mu1 minus mu2 equal to a particular number, I can replace this with that number, and then everything else is defined. So that's the key here, is that using the test, I can replace this term mu1 minus mu2 with the number in the null hypothesis, and then fix the type 1 error that way. Okay, so let's see, recall, if t is equal to z over the square root of, let's say, I don't know, w over, let's say, nu, like that, where z is standard normal, as usual, and w is chi-squared with nu degrees of freedom, and these are independent. Then t is t-distributed with nu degrees of freedom. So the challenge will be to show that this expression can be expressed this way, that there's a numerator, which is standard normal, and a denominator, which is chi-squared divided by its degree of freedom. Okay, so what's the distribution of y1 bar minus y2 bar? So we have y1 bar minus y2 bar. It's just the difference of two normals. This is mu1, so this is normal, mu1 minus mu2. And the variance of these is, and this is why we want the variances to be the same, otherwise it will not be perfect. But the variance is just the sum of these two variances. So this is sigma squared over n, sigma squared over n1, sigma squared over n2. So this is sigma squared 1 over n1 plus 1 over n2. Sorry about that. Okay, right. All right, so can we write t as having z on the top? So I have, so t, I have y1 bar minus y2 bar, and I have minus its mean. So if I divide by the square root of the variance, I then have a normal, right? So t is then equal to, And rather than write all that, I'm just going to go write z right now for this. So the top is z, right? Except I divided by the square root of this, right? I divided by the square root of this. So I have to do the same on the bottom, right? I can't just write z. I can't just divide the top by the square root of this. I have to divide the bottom by the square root of this too. So t is that, and then I have sp 1 over n1 plus 1 over n2 to the 1/2. And I have to divide by the square root of this on the bottom. So that's the same, right? If I am dividing by this, that's the same as multiplying it on the top, right? So I have I have sigma squared 1 over n1 plus 1 over n2. But I want the square root of this, right? So the square root of this. Okay, where z is normal 0, 1. Okay. Not bad. Well, look what happens. I have a standard normal in the numerator. In the denominator, this term cancels with this term. So the numerator, so t is equal to z over sp divided by sigma, right? Once I cancel this with this, and I can take the square root, I get sigma, and that's up here, but I can divide that, it's the same thing. Okay, what's sp is this over here, right? So I want to show that sp is chi-squared with, so we need to show that sp over sigma is chi-squared with n plus 1, n1 plus n2 minus 2 degrees of freedom divided by that, right? So we have t as this now, and now we're going to look at this piece. Okay, so let's look at the denominator. And note, these are independent. Since y bar, y2 bar, and s are independent, this implies z and sp over sigma. Okay, we never actually showed this in class, this independence, but we did mention it earlier, much earlier in the course. All right, so I need to show, to complete the proof, we need to show, must show sp over sigma is equal to a chi-squared random variable with n1 plus n2 minus 2 degrees of freedom divided by n1 plus n2 minus 2. Okay, that's all we have to do. Okay. All right. Okay. All right, so what do we have? We have sp over sigma. So, right. Okay. I want to show this is equal to the square root of this, right? Square root of this. So sorry about that. Okay. All right, so we have sp over sigma is equal to square root sp squared over sigma squared. Okay? Which is equal to sp squared removes the 1/2 power, right? So I get from the definition of sp, which is there. So we get this is equal to the square root sp squared, I get sp squared, the half power comes off, so I have n minus 1 s1 squared plus n2 minus 1 s2 squared all over sigma squared, and I'll take this out here now, so 1 over n1 plus n2 minus 2. Okay. Okay, very good. Well, these each are chi-squared. So n1 minus 1 s1 squared over sigma squared, we showed earlier, is chi-squared with n minus 1 degrees of freedom. Also, same, n2 minus 1 s2 squared over sigma squared is chi-squared with n minus 2 degrees of freedom. Now, when I add two independent chi-squareds, I get another chi-squared and their degrees of freedom add. Remember, chi-squared is just the sum of that many degrees of freedom. Standard normal squared. I got to put the indices in here, right? Okay. So this implies, right, that, so their sum, so are independent, so that their sum is also this should be minus 1, right? Sorry. Okay. So doing that, we have SP over sigma is equal to the square root, and I have chi-squared n1 plus n2 minus 2 all over n1 plus n2 minus 2. And the proof is complete. Okay, so